One of the most compelling and frustrating mysteries in the study of Earth's deep past is something known as the cool tropics paradox. This isn't just a puzzle about ancient temperatures, it's a clash between the tools scientists use to simulate the climate and the evidence they gather from the rocks, fossils and chemical traces left behind over millions of years. At its heart, the paradox highlights a fundamental tension between what computer models tell us about the Earth's climate during certain geologic periods, like the Cretaceous and the Eocene, and what proxy data suggest was actually happening in the tropical regions. These were times when the Earth had no ice caps, when the poles were warm and possibly covered in lush forests, and yet somehow the tropics seem to have been cooler than expected. To understand why this is such a big deal, you first need to get a sense of what we mean by a warm Earth period. During the Cretaceous, about 145 to 66 million years ago, and the Eocene, which began around 56 million years ago, global temperatures were significantly higher than they are today. Carbon dioxide levels were through the roof compared to our modern atmosphere, and the Earth was essentially ice-free. These periods are often referred to as greenhouse worlds, because of the high concentrations of greenhouse gases that trapped heat and made the planet much warmer overall. Climate models, which are essentially complex mathematical systems that simulate Earth's climate based on physics and chemistry, predict that in such warm conditions the entire planet would heat up fairly evenly. The poles would get much warmer, which they did, but the tropics, already warm, would get even hotter. According to many of these models, tropical ocean temperatures during these periods should have soared to over 35 degrees Celsius, maybe even higher in some scenarios. But here's where the paradox comes in. When scientists examine proxy data, like the chemical composition of ancient marine shells or the isotopic signatures in sediment cores, they often find that tropical temperatures appear to have been significantly cooler than the models suggest, sometimes in the mid to high 20 seconds Celsius. This isn't just a small disagreement, it's a major inconsistency that forces researchers to question either the accuracy of their models, the reliability of the proxies, or some deeper aspect of how climate actually works. This contradiction creates a rich area for scientific debate and exploration. On the one hand, climate models are built on fundamental physical laws. How energy moves through the atmosphere, how gases absorb heat, how oceans circulate. They have proven very effective in predicting modern climate patterns and can be tested against recent data. So, when these models consistently predict very hot tropical temperatures for ancient greenhouse periods, there's a strong assumption that they must be at least broadly correct. On the other hand, proxies are not to be dismissed lightly. These are the physical and chemical clues left behind in the geologic record. For instance, the oxygen isotope ratios in the calcium carbonate of foraminifera shells can tell us a lot about the temperature of the seawater in which those creatures lived. These are time-tested techniques, and when many independent lines of proxy evidence start to point in the same direction, in this case relatively cool tropical temperatures, it raises serious questions about whether the models are missing something important. So how do scientists begin to resolve this paradox? One line of investigation has been to re-examine the proxies themselves. Perhaps the tropical organisms whose chemical signatures we're studying weren't living in the open ocean surface waters as previously thought, but deeper down in the water column where it was naturally cooler. Or maybe the chemical reactions that formed those isotopic signatures were influenced by factors other than temperature, such as changes in ocean chemistry, salinity, or even evolutionary differences in how those ancient organisms formed their shells. Another possibility is that the models are simply overestimating the amount of warming that would occur in the tropics. While it seems logical that a warmer world would heat up evenly, the climate system is anything but simple. There are powerful feedback mechanisms that can limit warming in certain regions. For example, tropical cloud cover can act like a thermostat, reflecting sunlight and preventing surface temperatures from getting too high. Likewise, changes in ocean circulation might have distributed heat differently than the models assume, keeping the tropics relatively stable while the poles warmed dramatically. Still, others have suggested that perhaps the problem lies in how models represent convection, cloud formation, and moisture transport in the tropics. These are notoriously difficult processes to simulate accurately, even in today's sophisticated climate models. A small error in how clouds reflect sunlight or how moist air rises and cools could have a large effect on simulated temperatures. There's also the idea that Earth's climate system during the Cretaceous and Eocene was fundamentally different in ways we don't fully understand yet. Maybe the atmospheric composition included aerosols or trace gases that aren't accounted for in current models. Maybe the configuration of the continents and the ocean gateways influenced heat distribution more profoundly than we've appreciated. These variables could create regional climate effects that allowed the poles to warm while keeping the tropics relatively cool. Resolving the cool tropics paradox isn't just about setting the record straight for ancient history, it has real implications for how we understand climate sensitivity today. If the models are indeed over-predicting tropical warmth in past greenhouse periods, what does that mean for their predictions of future warming? Are we overestimating the degree to which certain parts of the Earth will heat up as CO2 continues to rise? Or are the proxies misleading us in ways we haven't fully recognized? This ongoing debate has spurred a lot of creative research. Some teams are building new, high-resolution models that attempt to simulate ancient climate with greater detail. Others are going back to the fossil record, searching for new proxy data from different regions or different types of organisms to cross-check existing interpretations. Laboratory experiments are also helping to refine our understanding of how certain isotopic signatures form under various conditions, which could help clarify whether these proxies are really telling us what we think they are. In recent years, there have been some efforts to reconcile the data by proposing that while the average tropical temperatures may not have been as high as models predicted, the extremes, the really hot days for example, might have matched or even exceeded the model predictions. In this view, the paradox is partly a matter of how we define and measure temperature. Are we talking about daily highs, seasonal averages, sea surface temperatures, or something else? It's possible that the models and proxies are describing different aspects of the climate and thus aren't directly comparable. Ultimately, the cool tropics paradox serves as a powerful reminder that science is an evolving process. It reminds us that our understanding of Earth's climate system is still incomplete, and that even our best tools, whether models or proxies, have limitations. It also highlights the importance of humility in science, the need to continually question assumptions, and the value of exploring inconsistencies rather than sweeping them under the rug. As we look to the future, with a planet that is once again warming rapidly due to human activity, understanding how the Earth responded to past greenhouse conditions becomes more than an academic curiosity. It becomes a way to test and refine the very models we rely on to predict what lies ahead. The cool tropics paradox may be rooted in the distant past, but its lessons are urgently relevant to the climate questions of today and tomorrow. And so the paradox remains a live issue in climate science, not because it lacks answers, but because it invites better questions. The more we probe this contradiction between models and evidence, the closer we come to a deeper, richer, more accurate understanding of how our planet really works. It's a story of disagreement, discovery, and the persistent drive to make sense of a world that is endlessly complex and surprising. The ancient Greeks were fascinated by paradoxes. From Zeno's infamous thought experiments to Parmenides' puzzling statements about being and non-being, they loved to explore the edges of logic and perception. One of the lesser-known yet surprisingly provocative paradoxes is something often referred to as a moving rose paradox, or more traditionally, the paradox of the stadium. Originally attributed to Zeno, this paradox plays with our understanding of motion, time, and the way events occur in space. At first glance, it seems like a trivial curiosity, almost like a logic puzzle that doesn't hold up under closer scrutiny. But the deeper one goes into it, the more unsettling and profound it becomes, touching on ideas of continuity, instantaneousness, and the nature of measurement. Let's set the stage clearly to see what the paradox is trying to tell us. Imagine 3 rows of identical objects, A, B, and C. Row A is stationary, like a fixed wall or line of posts. Row B is moving to the right at a constant speed, and row C is moving to the left at the same speed. The objects in each row are perfectly aligned and equally spaced. Now, consider a single object from row B and a single object from row C. At a particular moment in time, each of these moving objects passes a single object in the stationary, row A. So during what we might think of as one tick of time, let's call it an indivisible instant, each moving object passes exactly one stationary object. But here's the twist. Because rows B and C are moving in opposite directions, the object in row B not only moves past the object in row A, but also past an object in row C. Likewise, the object in row C moves past the object in row A and one in row B. So if we observe things closely, it looks like during this indivisible instant, the moving object in row B has passed two objects, one in row A and one in row C. But wait, row C's object is also moving, so from the perspective of row B, row C appears to be moving twice as fast relative to it. So in that same indivisible instant, did the object in row B pass two objects, or just one? And how can anything happen in an indivisible instant if, by definition, nothing can change during such an instant? This might sound like an abstract riddle, but the implications are surprisingly deep. What Zeno was trying to expose here is a contradiction in our assumptions about motion and time. If time is made up of indivisible instants, the smallest possible units of temporal measurement, then each instant is essentially timeless. That is, no change or motion can occur within a single instant because it has no duration. But if no motion can happen in an instant, then how can motion occur at all, since all motion is presumably composed of a sequence of such instants? Now, Zeno's framing of the paradox relies heavily on the assumption that time can be broken down into discrete indivisible units. That view runs contrary to how we think about time today, where it's typically modelled as continuous. But the paradox still holds value because it challenges us to consider what we mean by motion in the first place. If two objects can move past each other in a moment that has no duration, then how can we meaningfully say that they moved at all? And if during that same moment an object moves past one thing but also relative to another, how do we account for the number of events that took place? One way to look at this is to think in terms of relative motion. Suppose you're standing on a platform and two trains move past you in opposite directions. Each train is moving at 30 miles per hour relative to the platform, but 60 miles per hour relative to each other. If you're on one of the trains, the other one seems to zip by at twice the speed. This is just a function of relative velocities. But Zeno complicates the picture by collapsing this interaction into a single moment, an indivisible instant, where the distances covered appear inconsistent depending on your frame of reference. From the perspective of row A, each moving object just passes one stationary object. But from the perspective of row B, it seems to pass two objects, one in row A and one in row C. This duality causes the paradox. It might seem like modern physics should be able to clear this up easily. After all, we now have calculus, relativity, and quantum mechanics. But the paradox is slippery. Calculus allows us to talk about instantaneous rates of change. Velocity, for example, is the derivative of position with respect to time. But calculus assumes that time is continuous, not composed of indivisible instants. So, if time is continuous, there are no moments. In the strict sense, Zeno imagines there are only intervals, however small. Within any interval, no matter how short, motion can occur. This view dissolves the paradox by denying its premise. There is no smallest instant. There is only change that occurs smoothly over time. But not everyone is comfortable with that escape route. Some interpretations of time, especially in quantum mechanics, suggest that time might indeed be discrete at the Planck scale, the smallest measurable unit of time, about 10⁻⁻⁴ seconds. Below this scale, time might not even make sense as a concept. If that turns out to be true, Zeno's paradox may return with new urgency. In a universe where time is granular, not continuous, how do we account for motion, which seems inherently smooth? Even in the realm of special relativity, Zeno's paradox can still spark interesting debates. In relativity, simultaneity is relative. That is, what one observer sees as two events happening at the same time, another observer might see as happening at different times. So in the moving rows scenario, the idea of two objects passing each other in a night indivisible instant becomes problematic. One observer might say they passed each other simultaneously with the stationary row, while another might see those events as occurring in sequence. Again, the paradox forces us to re-examine our assumptions about how time and motion actually function in physical reality. Then there's the question of what we mean by busing, passing, tassing. In the first place, if object B moves past object A in an instant, What does that mean spatially? Did they share the same position at that moment? Were their centers aligned? Were their boundaries touching? In a real physical sense, objects are extended in space. So passing might not be a point event, but a process that takes time. That would mean the paradox is rooted in an unrealistic abstraction, treating extended objects as though they were points and motion as something that happens in no time at all. This abstraction is common in thought experiments. We simplify things to make the logic easier to follow, but in doing so, we sometimes lose sight of the physical constraints that would make the scenario coherent. Still, that doesn't diminish the value of the paradox. Instead, it highlights how our intuitions about space, time, and motion are shaped by experience, not by the abstract logic of physics or mathematics. When we push those intuitions to their limits, as Zeno did, we often uncover tensions and contradictions that force us to think more clearly. So, what does the moving rose paradox ultimately tell us? For one, it shows that our everyday understanding of time and motion breaks down when we try to reduce them to their smallest possible components. It reveals the difficulty of reconciling relative motion with a concept of time that includes indivisible instants. It invites us to question whether motion is a series of discrete events or a smooth, continuous process. And it reminds us that even concepts we take for granted, like two objects passing each other, can be far more complex than they seem. In many ways, the paradox is more relevant than ever. In the era of digital technology, we're increasingly comfortable with the idea of discrete units. Digital time is counted in bits and clock cycles. Simulations break time into frames. Even in physics, some theories suggest that space-time itself might be quantized. Against this backdrop, Zeno's ancient thought experiment feels strangely modern. It asks whether motion can be real in a world composed of tiny, indivisible units, or whether true motion requires a continuous flow that no machine or equation can fully capture. In the end, perhaps the most valuable thing about the moving rose paradox is that it doesn't have a neat resolution. It lingers, a philosophical itch that can't quite be scratched. It shows us that even in our most precise sciences, there is room for mystery, for contradiction, and for the kind of imaginative thinking that refuses to settle for easy answers. Zeno may not have known about calculus or relativity, but he understood something profound, that the universe doesn't always yield its secrets to common sense. Sometimes, the closer we look, the stranger things become. Imagine trying to find the location of everything that exists. That might sound straightforward at first. After all, we routinely describe where things are. Your coffee mug is on the table is in the kitchen is in your house, and your house is in your neighborhood. But if we keep following that trail long enough, a strange and unsettling problem begins to emerge. Where is space itself? Where is the universe? If everything that exists must exist somewhere, then that somewhere must itself be something that exists. And if that place exists, surely it must exist in some other place, and so on forever. This is the paradox of place. Originally posed by ancient Greek philosophers, especially the pre-Socratics like Zeno and Aristotle, the paradox of place cuts to the heart of our assumptions about space, containment, and existence. On the surface, it appears to be a simple question. If everything must be in a place, then what about the place itself? But the deeper we go into it, the more this question begins to unravel our everyday understanding of the world around us. Let's break it down. Start with an object, any object. A book, say, is on a desk. The desk is in a room. The room is in a building. The building is on a street. The street is in a city, and so on. Eventually, you scale this up to the planet Earth, which is in the solar system, which is in the Milky Way galaxy, which is in the observable universe. At each level, we describe the object as being in a container, a place that holds it. So we might ask, where is the universe? Does the universe exist in something else? If it doesn't, how can it exist at all? If it does, what is that thing in? This leads to an infinite regress. If the universe is in something, and that something is in something else, there's no end to it. We keep asking, what is that in, forever? That's the paradox. The very logic we use to understand the location of things seems to break down when we apply it to the largest scale. Now, this infinite regress isn't just a curiosity, it has real implications. If we insist that every existent thing must be in some place, and that no place can contain itself, and we can never find a final, ultimate location, the universe becomes like a set of nested dolls with no outermost shell. This clashes with our desire for completeness and closure. It feels wrong to think that there's no final place that contains everything. One way people have tried to resolve this is by redefining what we mean by place. Maybe place isn't a container in the traditional sense. Maybe place is a set of relationships. The book is on the desk not because the desk contains the book in some abstract spatial envelope, but because the book and the desk have a particular spatial relationship. This relational view of space can be traced back to thinkers like Leibniz, who argued that space is not a thing that exists on its own, but a way of describing the relationships between objects. In this view, space isn't something that needs to be in another space because it's not a thing at all, it's just a system of relations. But that still leaves us with a dilemma. If space is just a set of relationships between things, what are those things in? You could argue that they are in space, but now you've gone in a circle. The paradox creeps back in. If everything exists in space, but space is just the relation between things, then you're caught in a conceptual loop. You haven't escaped the paradox, you've just reworded it. Another approach is to consider space as something absolute. This was the view held by Newton, who believed that space was a real, physical entity that existed independently of the objects within it. According to this view, space is like a giant container, the ultimate stage on which all physical events occur. But even this view doesn't solve the problem entirely. If space is a container, then what contains space? If we treat space as a thing, then it seems natural to ask where that thing is. Some modern cosmologists argue that space doesn't need to be in anything. The universe, they say, is not in space, it is space. This idea gets even stranger when we consider that, according to general relativity, space itself can expand. The famous example is the balloon analogy. Imagine galaxies as dots on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they're moving through space, but because the space between them is expanding. But even this model raises uncomfortable questions. If the universe is like the surface of a balloon, then what is the balloon expanding into? If space itself is growing, where is it growing into? Some physicists argue that this is the wrong question. The universe isn't expanding into anything because there is no outside of the universe. The observable universe is all there is. But that still feels counterintuitive. We can't help but picture space as something that needs to be embedded in something else. It's how our minds are wired. We understand the world through metaphors of containment, cups holding water, boxes holding toys, rooms holding people. When we try to think beyond that, our cognitive tools start to fail. Quantum mechanics and quantum gravity add another layer of complexity. In some interpretations of quantum theory, space and time themselves are not fundamental. Instead, they emerge from more basic, non-spatial and non-temporal processes. In loop quantum gravity, for example, space is made up of tiny, discrete chunks called spin networks. These aren't bits of space in the traditional sense, but abstract structures that give rise to the appearance of space when viewed at large scales. If space emerges from something else, then asking where space is might be like asking where the number 7 is. It exists, but not in the way physical objects do. Then there are even more radical ideas, like those from string theory or holographic principles, suggesting that our three-dimensional universe might actually be a projection of information encoded on a two-dimensional surface. In these models, space is not what it seems. It's a kind of illusion, a useful fiction that emerges from deeper hidden structures. Again, if space is an illusion, then the paradox of place might dissolve. If there is no real place, then there's no need to ask what place is in. But such answers come at a cost. They require us to abandon our intuitive understanding of reality. They demand that we think of space not as a stage, but as a story, a narrative constructed by our minds or by deeper physical laws. That's a hard pill to swallow, and it doesn't make the paradox any less fascinating. In fact, it might make it more so, because now the paradox isn't just about space, it's about us. It's about the way we think, the metaphors we live by, and the limitations of our cognitive architecture. The paradox of place also has metaphysical implications. If everything must be somewhere and there's no final pent where, then maybe our very concept of existence is flawed. Maybe things don't exist in the way we think they do. Perhaps existence is not about being in something, but about participating in a network of relations, processes, or events. This resonates with some Eastern philosophical traditions, which view the world not as a collection of objects in space, but as a flow of interdependent phenomena. In such views, the question, where is it, becomes less important than what is it doing, or how is it connected. In the end, the paradox of place remains unsolved, not because we lack information, but because it exposes a deep tension in the way we frame questions about the universe. It reveals that our basic categories, space, place, containment, may be inadequate for the task at hand, and yet we can't escape them. They're built into our language, our thought, our very way of being in the world. So the paradox lingers, like an itch we can't scratch, a question we can't quite answer. Where is the universe? Where is place? Where is the where? We might never know. But in asking, we learn something valuable, not just about the cosmos, but about ourselves. We learn that the universe is not a simple nesting doll of containers, but a mystery that challenges us to think beyond what we can see, touch, or even imagine. And in that challenge, there is a strange kind of beauty. Let us imagine a silent room. In this room, you drop a single grain of millet to the floor. Nothing happens. Or rather, something happens. The grain falls, gravity does its work, and it hits the ground. But nothing audible registers. No sound is heard. Now, in the same room, you drop 1,000 grains of millet. This time, you hear it. The soft patter of grains falling becomes a distinct sound. And this brings us to a very old, very strange question. If one grain makes no sound, how can many of them, all equally silent, produce sound together? This is the paradox of the grain of millet. The paradox was famously raised by Zeno of Elea, the same Greek philosopher responsible for the paradoxes of motion, like Achilles and the tortoise, or the arrow that never moves. Zeno had a knack for teasing apart assumptions that we take for granted. The grain of millet paradox might not seem as flashy as his others, but in many ways it's more deeply disturbing. It calls into question the very nature of emergence, quantity, and how we perceive the world. How can something arise from what seems like nothing? Let's begin with the basic contradiction. We believe that a single grain of millet makes no sound. It is too small, too light, its impact too faint for our ears to detect. But we also believe that if you gather enough of them, if you drop 1,000 grains, you will hear something. So the paradox asks, how can the combination of many silent things produce a noise? If each grain individually contributes nothing, where does the sound come from? This is not just a puzzle about sound. It's a philosophical problem about continuity and discreteness. It asks us to consider whether properties like sound, weight, or even existence itself are additive in a straightforward way. Can we sum up a bunch of zeros and get something that isn't zero? In mathematics, 0 plus 0 is still 0, no matter how many times you add it. But in real life, 1,000 imperceptible things seem to become perceptible. This suggests that our intuitive ideas about parts and wholes might be misleading. One way to approach this is to question the assumption that a single grain makes no sound at all. Perhaps it does make a sound, just one too quiet for us to hear. Maybe the sound is there, but it falls below the threshold of our perception. In this view, each grain contributes a tiny sound, a whisper so soft it escapes detection. Add enough whispers together and you get a murmur. This seems plausible, and it aligns with what we know about sound as a physical phenomenon. Sound is caused by vibrations in the air. When a grain hits the ground, it produces a small disturbance in the air molecules. If that disturbance is strong enough, and if our ears are sensitive enough, we perceive it as sound. So if a single grain produces a tiny vibration, and many grains produce many vibrations, then eventually the cumulative effect crosses the threshold into audibility. The sound was always there, it just needed enough volume, both in quantity and intensity, to become noticeable. But this answer, while comforting, doesn't resolve the paradox entirely, because the real question isn't just about physics, it's about logic and perception. Even if we accept that each grain produces a tiny sound, we are still faced with the question, how do imperceptible elements give rise to a perceptible whole? This touches on the more general problem of emergent properties, how a system can have qualities that none of its parts possess individually. This is a big deal in philosophy, science, and even consciousness studies. Emergence is everywhere. Water is wet, but a single H2O molecule is not. A brain is conscious, but a single neuron is not. Society has a culture, but a single individual does not encompass that culture. The paradox of the grain of millet is a simple, elegant version of this problem. It asks, at what point does quantity become quality? Where is the tipping point between nothing and something? Let's think in terms of thresholds. Many phenomena in nature and perception operate on thresholds. A single photon of light may not be visible to the human eye, but enough photons will trigger a visual response. The same goes for touch, taste, smell, and hearing. These senses are not infinitely sensitive. They have limits. So perhaps what the paradox reveals is not a contradiction in reality, but a limitation in us. We do not hear a single grain because we are not sensitive enough, not because the grain is truly silent. But even that doesn't exhaust the puzzle, because the paradox also challenges our understanding of summation. In math, we might describe a quantity as a sum of many small parts. But when the parts are so small as to be nothing, or at least nothing perceptible, how do they amount to something that is? This is reminiscent of the Sorite's paradox, or the paradox of the heap. If you remove grains of sand from a heap one by one, at what point does it stop being a heap? Or if you add single grains to an empty space, at what point do they become a heap? There is no clear boundary, no sharp line. The transition is gradual, vague, and fuzzy. The grain of millet pushes us to confront the nature of continuity. Is the world made up of discrete bits, or is it a smooth continuum? If it's discrete, then there must be smallest possible units, smallest sounds, smallest movements. But if it's continuous, then there is no smaller sound, just smaller and smaller ones. And that would mean the notion of a soundless grain is flawed. It must produce some sound, however faint. But then we fall into the trap of the infinite. An infinite number of infinitely small things may still add up to something finite and tangible. Modern science leans toward this latter view. Sound is a mechanical wave, and even the smallest impact can, in principle, create a disturbance. Whether we hear it or not is a separate issue. So from a physical perspective, each grain does make a sound. It's just not one we can detect without extremely sensitive equipment. This seems to deflate the paradox, until you remember that Zeno wasn't just making a point about sound. He was making a point about the disconnect between logic and experience. Because even if we know intellectually that a single grain makes a sound, our experience tells us otherwise. We drop it and we hear nothing. We drop 1,000 and we hear something. Our senses do not register the individual components, only the result. So what we experience is a jump from silence to sound, from nothing to something, with no clear point at which the transition occurs. That cognitive gap is the true heart of the paradox. In many ways, this is a paradox about perception itself. Our brains are not designed to track infinitesimal changes. We work with categories, thresholds, and generalizations. Something is either silent or not, either a sound or no sound. But the world doesn't operate in binary terms. It flows in gradients, shades, and nuances. The paradox of the grain of millet reminds us that our perception of reality is not the same as reality itself. We live in a world of approximations. There is also an epistemological dimension to this paradox. It raises questions about how we know things and what it means for something to be real. Is a sound that we cannot hear still a sound? Is a thing we cannot detect still part of our reality? The philosopher George Berkeley famously argued that to be is to be perceived. If something cannot be perceived, does it exist? The grain of millet forces us to wrestle with this question. If a grain falls in a forest and no one hears it, does it make a sound? This paradox also speaks to the problem of aggregation. In social sciences, economics, and even politics, the behaviour of the whole is often not predictable from the behaviour of the parts. An individual may have no power, but a mass of individuals can form a movement. A single vote may feel meaningless, but millions of votes decide governments. This leap from the invisible to the visible, from the insignificant to the impactful, echoes the grain of millet. It reminds us that change often happens incrementally, and that many small nothings can accumulate into something transformative. It's also worth noting how the paradox plays into our emotional lives. Think about kindness. A single kind word might seem trivial, but 1,000 kind words? That might change someone's life. Or consider stress. A single irritation might be easy to ignore, but 1,000 small stresses? That might lead to burnout. The grain of millet is not just a curiosity from ancient Greece, it's a metaphor for how reality accumulates meaning, consequence, and sound through repetition and accumulation. The paradox, then, is not merely a challenge to logic or physics. It's a mirror held up to the way we understand the world. It reveals the gaps between perception and reality, between logic and experience, between the individual and the collective. and it forces us to ask whether the boundaries we draw between sound and silence, between something and nothing, are real or just mental conveniences. In the end, the paradox of the grain of millet leaves us with a profound insight that the world is built from things so small we may never notice them, and yet, together, they shape everything we know. It teaches us to look closer, to listen harder, and to remember that even the quietest things have a voice, if only we have ears to hear it. Let us take a moment and step into a world where imagination rules and physics bows to thought experiments. Here, we entertain questions not because they lead to definitive answers, but because they illuminate the limits of logic and language. One such riddle, deceptively simple yet infinitely deep, is the irresistible force paradox. It poses a question that seems to demand resolution, but simultaneously resists it with a kind of elegant defiance. What would happen if an unstoppable force collided with an immovable object? This question has existed for centuries, deeply embedded in both Eastern and Western philosophical traditions. It appears in ancient Chinese philosophy as the confrontation between a spear that can pierce anything and a shield that can stop anything. The paradox is also found in classical logic discussions, where it stands as a sort of mental trap, exposing the contradictions that arise when we attempt to stretch definitions to their absolute extremes. The irresistible force paradox does not merely challenge physical principles, it lays bare the weaknesses in our conceptual framework. To approach the paradox, we first need to unpack the definitions it relies upon. What does it mean for a force to be irresistible? In everyday language, it suggests a force so powerful that nothing can stop it, no matter what it encounters. Similarly, an immovable object is defined as something that cannot be moved, regardless of the force applied to it. Already, we begin to see the trouble. Both definitions are absolute and mutually exclusive. If such entities existed, they would be defined specifically in relation to each other. One can resist anything, the other cannot be moved by anything. When they meet, we are not witnessing a physical phenomenon, but a logical contradiction. In the physical universe we inhabit, there are no true absolutes in the sense this paradox demands. All forces are finite, all objects can be moved under the right conditions, given enough energy or change in circumstances. Even the mightiest stars can be displaced, destroyed, or reshaped under the colossal pressures of cosmic events. The very idea of an immovable object contradicts our understanding of the physical universe, just as the notion of an unstoppable force defies the principles of energy conservation and relativity. If a force is applied, it must be met with some kind of resistance, some kind of interaction that absorbs, reflects, or otherwise engages with that force. From the perspective of physics, force and motion are part of a system. Newton's laws tell us that forces result in acceleration unless they are balanced by other forces. Objects stay in motion unless acted upon, and resistance is always part of the equation. You cannot isolate an irresistible force or an immovable object from this interplay. Even in relativistic physics, where objects approach the speed of light and mass increases exponentially with velocity, no particle or wave escapes the system. Everything is connected, reactive, responsive. So in that sense, the paradox collapses. The definitions cancel each other out. If an irresistible force exists, then no object can be immovable. And if an immovable object exists, then no force can be irresistible. They are mutually exclusive by definition, and their coexistence is a logical impossibility. To even ask the question is to create a contradiction, like asking what lies north of the North Pole, or whether a square can be round. But this doesn't mean the paradox is meaningless. Quite the opposite. Its value lies in the way it exposes the structure of our thinking. The paradox forces us to confront the limits of language, logic, and conceptual consistency. It reminds us that not all questions are valid just because they are grammatically correct. Some questions, when analysed, reveal faulty premises. The irresistible force paradox is a lesson in intellectual humility. It tells us that words have boundaries and that not all combinations of them result in meaningful or possible ideas. Interestingly, the paradox also functions as a kind of metaphorical device. In literature and psychology, the image of an unstoppable force meeting an immovable object is used to symbolize conflict, impasse, or inner contradiction. It is the clash of two absolute wills, the confrontation between opposing principles that cannot yield or be reconciled. Think of a political stalemate, a deeply entrenched emotional conflict, or an ethical dilemma with no clear resolution. These are the real-world echoes of the paradox, and they are no less potent for being metaphorical. In this context, the paradox becomes a story about confrontation, one where the inevitable meets the unchangeable and the outcome is uncertain. It might suggest that something must give, that one of the absolutes is not as absolute as it seemed, or it might suggest a third outcome entirely, a collapse, a transformation, or a redefinition of the problem itself. Perhaps the collision creates something new, something previously unimagined. In literature, this is the moment of catharsis, of crisis, that gives birth to revelation. The paradox also has implications in theology and metaphysics. Some theologians have compared it to questions about divine omnipotence. Can an all-powerful being create a rock so heavy that even it cannot lift it? This question, like the irresistible force paradox, exposes the self-contradictory nature of certain assumptions about power and capability. It challenges us to refine our definitions of omnipotence, not as the ability to do the logically impossible, but as the ability to do all things that are possible. Some philosophers have tried to resolve the paradox by rejecting the absoluteness of its terms. That is, they argue that no such entities can exist in the first place. To posit an irresistible force and an immovable object is to assume the possibility of infinite extremes, which are not grounded in reality. In this view, the paradox is more of a semantic illusion, like asking how many angels can dance on the head of a pin. It plays with concepts but doesn't describe anything real. Others have taken a more creative approach, imagining hypothetical universes where the laws of physics are different. In such a universe, could there be an unstoppable force and an immovable object? Perhaps. But even here, one must define the rules carefully. In a coherent universe, the laws must be internally consistent. You cannot have a universe where logic breaks down, where contradictions coexist. So even in a fictional realm, the paradox remains a limit case, a boundary that cannot be crossed without tearing the fabric of the system. There is also a relational aspect to the paradox worth considering. The concepts of irresistible and immovable are not absolute in themselves. They are relational. A force is irresistible to something. An object is immovable against something. Without a reference point, these terms lose meaning. It is the interaction that defines them. This suggests that the paradox dissolves once we realize that both entities derive their identities from their relationship to each other. If they are truly opposed, then their very definitions collapse under the weight of their contradiction. The paradox teaches us about systems thinking. No object, no force, no idea exists in isolation. Everything is part of a network of interactions, influences, and conditions. To posit an irresistible force is to posit a universe in which all resistance can be overcome. But in such a universe, an immovable object is by definition impossible, and vice versa. This is not a limitation of physics. It is a recognition of systemic coherence. The irresistible force paradox might also be seen as a reflection of human experience. We often encounter situations that feel like impasses, where opposing desires, beliefs, or principles collide with no clear resolution. In these moments, we are living the paradox. And just as in the thought experiment, something must give. Either our understanding shifts, our perspective broadens, or we find a way to redefine the terms of the conflict. The paradox doesn't tell us what will happen, but it urges us to think differently, to imagine new possibilities. In the end, the irresistible force paradox is not a question to be answered, but a mirror held up to the way we think. It reveals the fragility of absolute language, the dangers of unchecked assumptions, and the need for contextual relational understanding. It challenges us to move beyond binary thinking and to embrace complexity, ambiguity, and nuance. It reminds us that not every question has an answer, and that sometimes the asking is the point. So what happens when an unstoppable force meets an immovable object? Nothing and everything. The universe cannot contain both, and so the paradox breaks down. But in the space of that breakdown, in the tension between impossibles, we find a rich field of reflection. We find philosophy, wonder, and a deepened awareness of the limits of our knowledge. And that, perhaps, is the most powerful force of all.